All right, so again, universal gravitation, force of gravity, weight of the object, universal gravitation constant, big G, 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared, times the mass of the first object, mass of the second object, over the distance between them squared. And now, because big G is a constant, we're going to pretend like it's not there and use this. We're going to convert both masses as a 1 and distance as a 1. So it doesn't matter what the original force is, because if we can change these values, all right, from like 1 to 2, because they said something doubles, and we play it out, you'll wind up seeing it'll give you the ratio of what happens to the force. Does the force double, triple, quadruple, get cut in half, get cut in a fourth, get cut in ninths? So here, two objects, same mass. So these are the masses. Since the mass does not change, we're going to leave both of them a 1. They said the distance triples. So remember, as distance apart, right, as the distance between the objects gets bigger, the force is going to get smaller. Masses don't change. All right, so 1 times 1 is, and 3 squared, and boom. So you are 1/9 of the original force, and so you would then circle or highlight 1/9 as great. Okay, this one's super quick, super simple. I asked you guys to use 10 for G. So all you're doing is taking the mass of 50 students, timesing it by the acceleration of Earth. All right, so 500. If you use 9.8, you can multiply by 9.8, but we're using 10 just for the simplicity of the calculation. So this one should be 500. Number 3, 1 meter separates two equally sized masses. If one mass is doubled, what happens to the new force? Okay, the masses are both of these. Now, it doesn't necessarily matter which one you change. All right, one mass doubled, so we're going to make this one a 2. They didn't tell me anything happened to the other one, so I leave it a 1. Did they say anything about the distance? No, so we're going to leave that a 1. Now, remember, distance always has to get squared. 2 times 1 is 2. 1 squared is 1, so it's 2 over 1, or just 2 times the original force, Fg. So the answer here is letter B. Number 4, space probe, mass of 5 kilograms on surface of Earth. They want to know what the mass would be at a spot where gravitational acceleration is 2 meters per second squared. I wrote in parentheses, guys, trick question. Why?
Because it's
Still 5 kilograms. Yes, your mass doesn't change. If I took, say, this highlighter, it's on Earth, and I teleported it to the moon, it's still going to be this exact same thing. All right? The whole mass of it is going to be the same. It's going to have a different weight, because weight is equal to an object's mass times the gravity of, right, wherever we're at, wherever the planet is. So this one is just the same mass. Five, astronaut has a mass of 60 kilograms and a weight of 12 newtons at a certain spot in space. What is the acceleration due to gravity at that spot? So you're given the equation Fg is equal to mass times gravity. Solve for G. So to get G by itself, divide both sides by m. So you take the force of gravity, or the object's weight. Right? Fg is the force of gravity, or an object's weight. And we divide it by the mass. 12 newtons over 60 kilograms. And we're going to get 0.2. And since it's little g, meters per second squared. Okay, planet X, twice the mass of Earth and twice the radius. Okay, so if your original weight was 500, what would your new weight be? Well, this planet has twice the mass. Your mass isn't changing. But they also tell you that the radius of the planet doubles. So that will be our d in the equation. Remember that d has to be squared. So what's 2 times 1? 2 squared. And 2/4, guys, reduces down to what? 1/2. So you would be 1/2 the original force. What was the original force? And the problem says your original force or original weight was 500. So what's 1/2 times 500? 250 newtons. Very good. Okay, imaginary star Z, 1/5 the radius, but has 1,000 times the mass. How much would a mass weighing 1 Newton on Earth weigh at star Z? So we'll do this. You're going to take the mass of the one object, okay, 1,000 times. So the other mass we'll just say is not changing. And then we have 1/5 on bottom. Now that has to get squared. So how I would do this in my calculator would be 1,000 divided by, and I'm going to put it in parentheses, 1 divided by 5 squared equals, and it kicks out an answer here of 25,000 newtons. Okay, satellite moves in a circular orbit around the planet. What do we have for this one? Okay, anybody else get something different? All right, well, I saw a couple people have velocity, and I saw a couple people with acceleration. So if this thing is moving around clockwise at any single point, let's say these 3 here, you have velocity, which is tangent at these spots. Velocity is essentially, guys, speed of the direction. So is the direction moving around in a circle constantly changing? Yeah. So it can't be velocity. Technically, if your velocity changes, the object is accelerating. So it can't be acceleration. And displacement is how far you are from the start. Well, let's say you started right there. You go around, yeah. Is your displacement constantly changing? Yeah. So can you be moving in a constant speed, though, moving around in a circle? Hell yeah. Hell yeah is right. Speed. Now, we get to the next side. There we go. Gravitational force of attraction between 2 objects would increase. All right, so I'm going to use the 1's equation for this. Remember, right, that these will basically be mass of one object, mass of the second object over the distance between them squared. I left out big G for a reason, because it's a constant. It's not going to affect this. Double the mass of both objects. Well, if masses are on top, if I double both of them, what's 2 times 2 over 1 squared? 2 times 2 is 4. 1 over, it would be 4 times the original force. So A would increase, yes, it would be 4 times. What if I double the distance between the objects only? Well, if I doubled only the distance, the masses don't change. The distance would become twice as big. We have to square it. 1 times 1 is 1. 2 squared is 4. So we would have 1/4 of the original force. So does that increase? No, definitely not. What about the next one? Both masses are doubled. And the distance between them is doubled. So 2 times 2 on top is 4. 2 squared is 4. This can reduce to 1. So This isn't an increase because it's the same value. It would be the same value. Doubling the mass of one object and then doubling the distance. So only one of the masses change. Remember, masses are on top. Since it doubles, it becomes a 2. The other one doesn't do anything, so we keep it a 1. And then they say double the distance. So this d, which was originally supposed to be a 1, we make it 2. We have to square it as the equation. 2 times 1 is 2. 2 squared is 4. So this reduces to 1/2 the original force. So this is a decrease. This one is a no change. This one is a decrease. The only one that actually increases is letter A. All right, again, what you're doing here is you're using the one equation and manipulating everything that you need to. Okay. So for this, distance between centers is quadrupled. So what am I going to change there? Do I change either of the masses? No. So they're the two ones on top stay ones. But what did they say changed? The distance. It what? Quadrupled, so it would be times by 4. So the 4 would go on the bottom. But in our equation, d is squared. 1 times 1 is 1, and 4 squared, 16. So you are going to have 1/16 of your original force or original weight. All right, those ones are basically done the exact same way. The rest of them, B through E. One is made 5 times larger, so this one I'm just going to do a little bit quicker. One of them is multiplied by 5. The mass doesn't. One of the other mass doesn't change, and the distance doesn't change, so this becomes 5 over 1, or 5 times the force. One mass becomes 1/3 the original. The other mass doesn't change, and the distance doesn't change. This one? That's okay. So if they tell you to cut a mass like this to make it 1/3 of something, yeah, you would just write as like 1 times 3, right? 1 divided by 3. Times 1 is still going to leave you with that 0.33. Divided by 1 squared. 1 squared is 1, so it's still going to wind up giving you this whole thing as 1/3 FG, or if you put 0.33 repeating F sub G. Either one of those works. One mass is doubled, the other is tripled. One of them becomes a 2, the other becomes a 3. Nothing changes about the distance. So this one becomes 2 times 3, 6 over 1, or 6 times the force. Both are doubled, and distance are doubled. Both masses doubled, so 2 times 2 on top, 2 squared on bottom. 4 over 4 reduces to 1. So it would just be the same. Gravitational force between two objects is 60. So this 11 is just like number 10. Instead of putting Fg, you would replace Fg with 60 and then multiply that. So for example, if one of the masses is tripled, one of them becomes a 3, the other doesn't change, and distance doesn't change. 3 times 1 is 3, and 1 squared is 1, so this would be 3 times the original force. If the original force is 60, what's 3 times 60? Or what's 3 times, yep, 180. If one of the masses is halved, okay, well, we put a 1/2 up top for one of the masses. The other one doesn't change. Keep it a 1. Distance didn't change. Keep it a 1. And this is going to wind up working out to be just 1/2 FG. Thank you. 1/2 of 60. 30 newtons. We're going over the homework right now. Distance between their centers is tripled. Well, 1 times 1 on top because mass doesn't change. And then we got next, this 3 is squared. 1 times 1 over 3 squared. It's 1/9 the original force. So you do 1 divided by 9 times 60. Comes out to be like 6.67 or 6.66 repeating. So we cut it off like that. All right, the next one's easy. The next one after that is easy. The only one that should be a little bit trickier going forward is F. If one of the masses is made to be 1/3 the size, and the other one's made to be 4 times as big, they don't change the distance, so we keep that a 1 squared. 1 divided by 3 times 4, you can just throw that into your calculator. 1 divided by 3 equals this, times 4 equals this, divided by 1 squared, which is just 1. You're going to get 1.33 times the original force. So you do 1.33 times 60. And so you're going to be left with 80 newtons for that one. All right. And then the last one, same deal. It should be 1/16 the size. Yep. All right. So that, guys, would be how we complete those. So pretty simple. All right. Once you get the handle on realizing masses are the guys on top, distance is the guy on bottom, throw them down through ones and change them how they're telling you. All right. If masses are doubled, tripled, quadrupled, going 5 times the size, something's getting cut in half, something's getting the distance is doubling, but d is squared. You have to just make sure you do those properly. Okay.